Okay, back to discrete optimization, constraint programming part 1. Okay, so what we're going to see today is we're going to introduce one more trick in our bag. Okay, so I told you, optimization is a bag of tricks. Okay, we don't call them tricks, we call them methodologies or paradigms or computational paradigms or something. So this is one of the main paradigms to actually tackle optimization problems. Okay, so what I'm going to do today is basically giving you a very high level introduction to constraint programming. Okay, so the basic principles. Okay, very simple stuff. Okay, and the subsequent lectures are going to go into more and more detail and more complicated things. But the key today is intuition and what is really the essence of constraint programming. Okay. And so this is in 2 words, in one slide, what we're going to see. Okay, so constraint programming has 2 things which are interesting. First, it's a computational paradigm, okay, which is very different from dynamic programming and branch and bound that we have seen so far. So the key idea is what you want to do is look at the problem constraints, okay, and try to use them to reduce the search space. Okay, so remember when we saw branch and bound, we had this bonding technique, optimistic evaluation, and the goal there was to prune the search space by using the objective function. Here, we are going to prune the search space by looking at the constraints. And the constraints are going to tell you, ooh, that value, if this other value is taking that value, that variable cannot take that value. Okay, so that's what's going to happen. We're going to look at values which cannot appear in any, solution, any feasible configuration, and we are going to remove them, okay? And therefore, we're going to reduce the search space, okay? Completely orthogonal to the bonding techniques, and these things work together nicely, okay? Now, there is another thing which is very nice about constraint programming, and that's why we are starting with this one, is that we can model problems at a very high level, okay? So essentially, the key to designing good constraint program is to try to tell the solver as much of the problem as possible. Reveal the structure, okay? Don't try to use low-level encoding. Give the structure to the solver, then the solver can actually exploit it. So you'll see what that means. But essentially, what you want to do is express large problems in terms of substructure, things that building block. It's like playing Lego. Okay, so you're basically assembling this Lego together. Okay, and the reason is that you want to give the solver as much information as possible. Okay, so I'm going to start with a very simple problem, which is the 8 queens problem. Okay, so what you want to do is to place 8 queens on a chessboard. Okay, now the first time when I tried to introduce that problem to my dad to explain what I was doing, he told me, but I don't have 8 queens. I told, just pretend that you have 8 queens, but I don't have 8 queens. Now look, I have 8 queens now. Ooh, look, I have all of them. Daddy, you can actually play the game. Okay, so we have 8 queens. That's the beautiful of 3D printing. Okay, disclaimer: I have no shares in 3D printing companies, but this is kind of nice. Okay. Anyway, so this is what we are trying to do. Okay, so placing these 8 queens on a chessboard such that no 2 queens are actually attacking each other, which basically means they cannot be on the same row, they cannot be on the same column, and they cannot be on the same diagonal, upper and lower diagonals. Okay, so that's what we are trying to do. Okay, so this is the chessboard. Okay. There, and we are trying to place these queens. Okay, so let's look at what we're going to do. So this is the first queen. Okay, we place it there. Now the goal of constraint programming is to reduce the search space. We want to be sure that we remove values that are impossible. In this particular case, these values are impossible. No, we can't place any queens there. Why? Because they are on the same column. You can't place anything on the same row. That's what you see. And then we cannot place anything on the same diagonal. That's what you see there. Okay. So we place the second queen. That's the second queen that you see there. Okay. So once again, we do the same thing. We remove the values which are infeasible. Look, this search space is getting smaller and smaller. Okay. So we place the third queen, and now nice things are going to happen. Okay. So you remove values, same row, same column, and what you see at that point, okay, is something which is kind of interesting, right? So what do you see? Is that there is one queen here, one particular column, which has only one value left. So you know that you have to place that queen over there. So you can place it, okay? So you place that queen there because this is the only value that can be placed on that particular column, okay? And then you remove values, and then now what you can see is that, okay, so here you have to place a queen again, because this is the only queen that can place on this column, and you know that there has to be a queen on every column, because you have 8 queens and they cannot be on the same column, okay? And so essentially you place the queen over there, okay? And once again you prune the search space. You see that again you have to place that particular queen over there. You place it, okay? Now you propagate the constraints again, and you see that, oh, but at this point these are the 2 cells that are left, and I have 2 queens to place. So I know that given the first position of my first 3 queens, I can't place queens on these two cells because they're going to attack each other. So at this point, if I place the first 3 queens over there, I know that there are no feasible solution. Okay? So what I have done here, okay, is beautiful, right? So if I place these 3 queens just by propagating the constraints, by reducing the search space, I can detect that there are no solution with these 3 queens. Okay, so I made 3 positioned the way they are. So placing 3 queens here is basically automatically, by propagating these constraints, discovering that there are no feasible solutions. I don't have to branch on the 4th, on the 5th, on the 6th, on the 7th, and the 8th, and the last queen. Okay? So what am I going to do? I'm going to say, I can't place this queen over there. I'm going to reconsider a new position, let's say this one, and I'm going to restart the process, propagating the constraints again. Okay, and trying to see if I can find a solution. Okay, so you have seen the essence of constraint programming at this point. And the essence of constraint programming is essentially using the constraint to reduce the search space. And the search space here is essentially the set of values that the variables can take. Okay? And so what we have done is basically looking at which values can be removed without removing any feasible solution. We were always conservative, only removing that things that we know cannot be placed there. And when you do that, essentially, you reduce the search space as much as you can. And then once you are stuck, you will make a choice, okay? And that choice is going to start another set of propagation and another set of deduction, okay? And that's the computational paradigm. Now, there are many choices, okay? So what is a choice? It's going to depend on the various problems. But, at the beginning, we're simply going to assume that the choices that we deal with are basically assigning a value to a particular variable. No, there are many choices, and one of the things that you know is that in optimization, many of them will be wrong, okay? So if you have a choice and if it's wrong, we're going to do exactly what we have done in branch and bound. We're going to go back to a previous choice and, and reconsider it, and let's say assign a new value to a particular variable, okay? So that's the 2 assets here that we have, okay? So we have essentially constraint propagation for removing infeasible values from the domain of the variable, the set of values that the variable can take. And then we have the ability to make choices when we are stuck, when we can't deduce anything else. Okay? So let me illustrate this. So what I want to do now, so you have the essence. So this is essentially what constraint programming do. So what I want to do now is use an even simpler example, okay? And then look at the model and how essentially you can actually use the constraint for pruning the search space. So what we're going to look is, coloring a map. And so the key idea is that you have a set of territories here. They can be state, countries, whatever, okay? And you want to color them such that 2 adjacent territories are not colored with the same color. They don't receive the same color, okay? Now, there is a beautiful theorem. Actually, this is the first theorem that was proven with the help of a computer, that every map can be colored with 4 colors. So we'll never need more than 4 colors, okay? So, and essentially, what we have to do is write a program which, given a map, okay, and list of adjacent territories, is going to color the map such that no 2 adjacent territories are going to receive the same color. So this is this is essentially what we're going to do. And so once again, what we do is we have to find what the decision variables are. With any kind of methodologies, that we will explore, like local search, like constraint programming, like mixed integer program, the first step is always going to be choosing the decision variables, okay? And then expressing the constraints in terms of the decision variables. What are going to be the decision variables here? Well, for every one of these territories, you will have a decision variable, and that decision variable is going to tell you what is the color of that particular territory or country if we are modeling a map of countries, right? And then the domain of these decision variables are going to be all the colors, okay? So since we are in the map, okay, we know that we need only 4 colors, so we'll choose them, blue, red, green, and brown, whatever, okay? So 4 different colors, that's all we need. And now the constraints are going to basically specify that 2 adjacent territories cannot have the same color, okay? And the best way to do that is use, a not equality constraint. Okay, so this is a model, okay? So this is a model in a high-level modeling language, and I'm going to go over, some of these aspects. So what you have there is that you have an enumerated type which tells you what are the countries that we are interested in, okay? So this is a tiny subset of, the European countries. Okay, and in this particular case, we're going to use also a list of colors. That's basically the values that the variables are going to take. And we take black, yellow, red, and blue. Okay, that's what you see over there. And the next line is basically telling you what the decision variables are. Okay, so what you see here is that you have a set of colors. For every country, there will be one color, okay, a decision variable, which is associated with every country. Okay, and that's essentially the color that that country is going to receive. And this is a variable which is ranging over the set of colors. Okay, so the values that every country can take is basically black, yellow, red, and blue. Now, what we are trying to do is solve. Okay, this is a feasibility problem. Okay, we are trying to solve, and find a solution which essentially use this 4 color and satisfy all these adjacency constraints. Okay, so you know that Belgium is adjacent to France, so we want to be sure that the color of Belgium is going to be different from the color of France. Okay, so you have this not equal constraint saying, okay, the value of these 2 variables have to be different. Same thing, between Belgium and Germany, and up to the very last, which is basically between Germany and Luxembourg. These 2 countries are adjacent, so you don't want them to be color with the same value. Okay, so that's essentially a high-level model of a constraint program. Okay, and you have these constraints that are basically specifying the relationship between these decision variables. Okay, so this is essentially this small part of Europe where you see all the countries. Okay, and at the beginning, what the constraint program is going to do is trying to prune the search space. But at the beginning, you can't prune anything in a sense because all the countries can take all the values. Okay, and so nothing is going to happen at the beginning. So these are all the possible values that these guys can take, all the possible colors. And then at some point, you're going to make a decision because you can't propagate anything. You can't reduce the search space. And you are going to color Belgian black. Okay? So once you do that, you can start pruning the search space. Because essentially, you know that all the adjacent countries, okay, cannot take the value black. Okay? And this is what is happening. Okay? You remove the value from the set of from the domain of these variables, so they can't take that value anymore. Okay? Now you color Luxembourg in yellow. That's the tiny pieces that you see over there, right? And so the adjacent countries to Luxembourg, okay, Germany, France, cannot be colored with yellow. So you're going to remove these values from Germany and France. And then you're going to color Germany, let's say in red. You're going to remove all red from all the adjacent countries. Okay, Denmark, the Netherlands and France. France is going to become blue. Okay, then you will have to choose a color from the Netherlands and Denmark, which in this particular case, are easy to do. Okay, so that's the way the constraint program is going to work. Okay, so once again, so those constraints, and I will tell you exactly the pruning that they do later on, but they will basically prune the search space the way I've shown you. Okay, once again, the computational paradigm is using the constraint to reduce the search space. When you're stuck, okay, you basically make a choice. The first choice that I've shown you is coloring Belgium in black. Okay, so in the particular coloring problem, at the beginning there was no search space reduction. There was nothing you could propagate it, and I will tell you why later on, right? And then afterwards, what happened is that you gave a particular color. You gave a particular color to Belgium, okay? So you gave the color black, okay? So when that happens, essentially you look at these constraints in which Belgium appears, okay? And so essentially these constraints can be rewritten, by replacing, the decision variables of Belgium by black. And now what you see is that all these constraints are turning into, France has to be different from black. Germany has to be different from black. And those are very easy, constraints to deal with, because at this point, if you want to satisfy these constraints, the only thing that you have to do is to say, France can take all these colors. If France can still take the color black, I have to remove it, because if it takes the value black, this constraint is not going to be satisfied. So you can use these constraints to start pruning the search space. And that's what the constraint programming system does. Okay? So that's what's going to happen. Oops, look at this. So, I'm go back. So you give that, and you remove the value of these variables. Okay? So once again, so when you think about constraint programming, it's not a branch and bound framework. It's called a branch and prune framework, in the sense that what you do is you prune the search space, but you don't use a bounding technique to do that. What you do is you use the constraints to remove the value from the variables, from the domain of the variables. And once again, when you're stuck, you decompose the problem. It's like the branching part of branch and bound. Okay? And the pruning is based on essentially feasibility information. You look at the constraints and you try to remove value that cannot appear in any solution. Okay? Remember when we had this constraint, France has to be different from black, the color of France has to be different from black. What that means is that we want to, when we remove the value black from the domain of France, we know that this is a valid inference, that we can do that. We are not removing any solution because if France was black, that constraint would be violated. Okay? So, a couple of things that I have to mention, constraint programming is a complete method, okay? So it's going to find a solution if one solution exists. It can find all solutions if you want all of them. And if you are in an optimization problem, it will find the optimal solution. And I will come back to this later on how we do optimization using constraint programming. But one of the key things is that this technique, this methodology, this computational paradigm can find optimal solution, has always a guarantee that it will find a feasible solution or the optimal solution. Of course, it may have an exponential behavior, which means that it can actually take a long time to get it. But if you give it enough time, it will always find a feasible solution. It will always find an optimal solution in an optimization problem. Okay? The focus, this is the other things that I have to tell you, the focus in constraint programming is on feasibility. Okay? It's basically, how to use constraints to prune the search space. Okay? So it's a very different focus than branch and bound, where the focus is on bonding, is finding this optimistic evaluation and its relaxation. Here it's different kinds of relaxation in a sense, and what we focus on in feasibility and removing as many values as we can from the domain of these variables. Okay? So this is a way you can view a constraint programming system. You have a search, okay, and you have a constraint store. What you're trying to do all the time is, can I satisfy this constraint? Can I satisfy this constraint? Okay? And then when you're stuck, when you say, okay, I can satisfy the constraint, but I cannot prune the search space, what the search is going to do is add a new constraint. And the constraint store is going to say yes or no. Okay, am I still satisfiable or not? Okay, and so in this particular case, it says, yes, I'm satisfied, you can continue. Okay, and sometimes, the search is going to send another constraint, and then you say, no, I have violated, my constraints are violated. Give me another constraint. Okay, remove that one and give me another one. Okay, so this is the inside of a constraint programming system. Okay, so what you see there is essentially the search space representation, the domain store. That's essentially the domain of all the variables. And what you see gravitating around it are the constraints. Okay, and this is kind of interesting, right? These constraints are only interacting with the search space. They are always trying to say, can I remove values there? Am I feasible? And we'll come back to that in a moment. But they don't know about each other, and that's both a strength and a weakness. Okay, so it's easy to add new constraints because they don't interact with the other ones. They just interact with this representation of the search space. Okay? So I alluded to this already. What does the constraint do? A constraint has two goals in life. One of them is checking feasibility. So the constraint is always looking at the domain store, at the set of possible values that the variables can take. And it's always asking, am I feasible? Can I find a solution to myself? Okay, so that's feasibility checking. So we always try to see if any one of these constraints is feasible independently of the other ones, right? So you look at one constraint in isolation and you ask yourself, can I satisfy this constraint? Can I find a solution? That's the first thing you always do with these constraints. And the second goal in life for a constraint is to prune the search space. They're going to look at this search space and they say, can I knock down some values there? Because then my search becomes smaller, and that's how you can curtail this exponential growth. Okay? So the second goal of pruning is basically looking once again, constraints in isolation and seeing, to be satisfied, I have to remove these values in the domain of those variables. Okay? And that's what you do. That's what the constraint does. You have these two things, feasibility checking, making sure that the node that you are exploring is potentially feasible, and then pruning, trying to reduce the set of values of the various variables. Okay? I talked about this. Basically, this is basically summarizing what I just said. Okay? Of course, you only prune when you know that you're feasible. You will never try to prune when you are already in an infeasible state. Okay? Now, the core of a constraint programming system is this propagation engine, okay? And the way to think about it is it's as a very simple iterative algorithm, fixed point algorithm, where the constraint engine is going to take one constraint and say, are you feasible, okay? And if the constraint is feasible, it's going to tell the constraint prune. And so the constraint is going to prune the search space. And then the engine is going to select another constraint and say, are you still feasible? Okay, can you prune the search space? And the engine is going to continue doing that with all these constraints. Are you feasible? Can you prune? Okay, until there is no values that can be removed from the domain of any variables. So then you reach this stable state, which is called a fixed point, right? And then you know that at this point you have inferred as much information as you can. Okay, and so the system will typically go back to the search component and ask, "Oh, make a choice because I'm stuck at this point." If you haven't found a solution so far. Okay, so that's basically the key. So the key is basically this propagation engine, which is basically selecting constraints, asking if they are feasible, and then if they are feasible, asking if they can prune the search space. Okay, so if we come back to this beautiful 8 queens problem, right? So my beautiful queen. Right? And so I'm basically asking, so what are the decision variables? And I told you that before. There are many, many different modelings, okay, so of any kind of optimization problems. And the 8 queens problem is one of these problems where you have many modelings. So I'm going to show you one of them, okay? But there are many, many others. And that's what makes optimization very interesting in general, because you have to find out, which model am I going to use? Is it going to be good or not? And so on and so forth, okay? And we'll see what it means to be good or not. But in a sense, will I be efficient? Will I explore a small part of the search space? So I'm going to show you one modeling of the 8 queen problems. And the key idea there is that I'm going to associate the decision variables with every column. I know that I have to place 8 queens. I know that the queens cannot be on the same column, otherwise they would attack each other. So I know by definition that I can associate a queen with every column. Okay? And therefore, what the decision variable is going to do for every column is going to decide which row the queen on that column is going to be placed on. Okay? So decision variable, 1 queen per column, and the decision variable is denoting the row for that column on which the queen is going to be placed. Okay? So these are my decision variables in this particular case. Now, what are the constraints? There are 3 types of constraints. So now that we have a queen which is associated with every one of the column, we have to make sure that they are not placed on the same row. Okay? Otherwise, they would attack each other, and not on an upward and a downward diagonal. Okay? So yeah, that's what I said. Okay? And so what you see here is, once again, a high-level constraint programming model to do that. Okay? So we basically, this is for the 8 queens, so we have a range from 1 to 8. Okay? That's basically the 8 column. Okay? So now we have a decision variable which is called row. Okay? For every one of these columns, I have to associate a row with that column, and there are 8 rows, so that's the set of values that particular variable can take. And what you see over here are all the constraints. And what I'm basically doing for stating these constraints, I take two rows, 2 columns, I and j, okay? And I'm basically assuming that I is, smaller than j. And then I'm basically specify that they cannot be on the same row. They cannot be on the same, upper diagonal and lower diagonal. And that's what you see over here. Okay, so these are basically the constraints. And once again, they are like in the coloring. They are, not equal constraints. I'm basically saying that the row of I has to be different from the row of j. Okay, and then that the row of I is different from the row of j plus j minus I, which is basically giving you one of the diagonals. Okay, so these are the rows, these are the upwards diagonals that I was mentioning, and this is the lower diagonal. Okay, and I do that for every pair of queens, ordering them by I take I and then I take j, which is greater. Okay, so when you have that, what you may wonder is, what happens when I give the value 1 to a particular queen? When I place, the queen on column 1 to row 1. Well, these are essentially, what you see there, are essentially all the constraints. Okay, so I just expanded that model here into this set of constraints. When you give the value 1 to that particular row, so this is the expansion, right? So this is not on the same row, this is not on the same diagonal, this upward diagonal, this is not on the downward diagonal. Okay, and so now, if I give the value 1 to row 1, what's going to happen? Well, this constraint is going to become, row 2 has to be different from 1. Okay, so you will make sure that the second queen, the queen on the second column, okay, cannot be placed on row 1. That's what this constraint will do. The next constraint that you will see here is going to say that row 2 is different from 0. That's not useful because we know that 0 is not part of its domain. And the last one here is basically going to tell you that row 2 has to be different from 2. That's essentially the diagonal that's going up there, right? And so, well, actually, it depends the way you see the chessboard, but it's basically saying that it cannot be placed on the second row, okay? And you can use that for removing the search space from that value from the domain, and therefore reducing the search space. Okay? Once again, I told you that the two things that it does is feasibility checking and pruning. Okay? I'm going to skip this slide, but what I want to do here is basically telling you a little bit how this is done for the very simple constraints that we have considered here, for the map coloring and for the Queen's problem. Okay, so essentially we'll consider two variables x and y, and we're going to say that x can take the value between 0 and 2, and that y can take the value between 1 and 2. Okay, typically what we do, and in many of the lectures on constraint programming, that's what I'm going to use. We are basically saying that x, the variable x, has this domain 0, 1, 2, and that y has this domain 1, 2, 3. Okay, and so the domain essentially is the domain of x, okay, is going to be represented by dx, is a set of these values, okay? And so one of the goals is going to be trying to knock down values from this domain all the time, okay? Sometimes I'm going to use intervals as well to denote, 1 to 5, to denote the value 1, 2, 3, 4, 5. Boring, right? So, but this is a notation that I'm going to use from time to time. Okay, so let's look at the constraints. X has to be different from y, okay, so that constraints, and assume that the domain of the variables are this, okay? So one of the things that I have to do is to do feasibility checking. Is this constraint feasible? Obviously here I can see that it's feasible, right? I can take 0 there and 3 there, and it's going to be feasible, okay? So the general rule here is that what you do is you basically take the union of these two domains, right? And you look if the size of that union is greater than 1. If it's greater than 1, okay, so what that means is that I can take at least two values, okay? And therefore, the constraint is going to be feasible. Okay, so in this particular case, I can see that the size of this thing is 4. The union of them is obviously greater than 1, and therefore or greater or equal to 2, like I'm writing there. And then you are sure that this constraint is feasible. Okay, so this is all. So feasibility here is going to be very, very simple to achieve. Now, how do we do pruning? This is what I've shown you before, right? So essentially, the pruning in the example that I've shown is happening when a variable can take only one value, okay? If it has two values, essentially you can't prune. It happens only when a variable has only one value that you can start pruning the search space. If a variable can take only one value, you have to make sure that the other variable cannot take that value, and you remove it. And of course, that's symmetric. Whatever the value is, whatever the variable is, it will go from one direction to the other, or from the first variable to the next one. Okay. So if y has to have the value 2, you will remove 2 from the value of x. Okay. So that's how you do pruning. Now this is very, very simple, right? So this is a very, very simple constraint. One of the beautiful things about constraint programming is that constraints can be arbitrarily complex, and we'll see examples where the constraints itself is an optimization problem. And you still can use polynomial algorithm for actually pruning the search space. And we'll go into that, okay? So this is a really, really tiny example to show you the principle, feasibility checking pruning, but we'll see much more interesting example where feasibility checking and pruning are going to use very interesting algorithm. Okay? So see you next time. This was the first lecture on constraint programming. There will be many more to come with many more interesting things.